3, 2, 1. And we are live. All right, so let's get started. Welcome everyone to the final Universe at Home talk of this semester on irregular galaxies. So I guess we'll start with some introductions. So Mason, would you like to introduce yourself?
Sure. Hello, I'm Mason Huberty. I'm an undergraduate at the University of Minnesota, majoring in astrophysics, of course. And yeah, I do some research on galactic outflows, which I'll discuss a little bit because there's some prevalence in irregular galaxies here. And then, yeah.
Yeah, thanks, Mason. And my name is Derek Pereira. I am a first-year graduate student here at the University of Minnesota. I do not do research in irregular galaxies. However, I do find them very interesting. I instead do research on gravitational lensing. So let's go ahead and get started with the talk. So first, a primer on galaxy classifications before we dive right into the irregular galaxies. So there are two main types of galaxies, spirals and ellipticals. Spiral galaxies are by far the most common type of galaxy, making up about 60% of all galaxies in the universe. They're generally younger, and as a result, they look more blue and bright because they have more young stars. And they are characterized mostly by the spiral arms, which you can see in this top image here. This top image is of the galaxy NGC 1300, which is a common or an average type of spiral galaxy. They are formed in a actually very interesting way, it's known as the density wave formation, which I'm not going to talk about at all, but it comes up a lot in galaxy formation information, and it does influence the spiral structure that you see when you look at one of these. The other type of galaxy is an elliptical galaxy, which is characterized by a more ovular shape. These ones have little star formation because they're much older galaxies, and as a result, they look more red. They make up only around 15% of all galaxies, so they're by far not a common type of galaxy. And they're actually formed from galaxy mergers between two spirals. And now we can move on to irregular galaxies, which are basically neither spiral nor elliptical galaxies. These are also formed via galaxy collisions, but they are often from the younger types of spiral galaxies, and they have no structure, largely because when these collisions happen, they kind of erase all structure that was previously present. These can be split into three different types of irregular galaxies. Type 1s are known as the more normal type of irregular galaxies, which, if you can even call them normal. They lack a central bulge. However, there's some spiral structure present in a type 1 irregular galaxy. And type 2s have no structure at all. And they are not characterized by any type of prevailing structure, and then they are usually just completely blown apart during the galaxy collision. And the last type, which is an interesting one, is a dwarf irregular galaxy. Most dwarf galaxies are classified as irregular, and as their name suggests, they are very small. They have they have less gas than type 1s or type 2s, and they're very similar to the galaxies that were first thought to form in the early universe. One other interesting fact about dwarf irregular galaxies is that they lack elements that are greater than helium. In other words, they have a very low metallicity. As astronomers, we like to call any element heavier than helium a metal, even though that's not true in terms of chemistry. But that is one feature of dwarf galaxies that is used a lot in research. And on this image here on the left, that is of NGC 1427A, which is a dwarf galaxy that I will also be talking about later on in the talk.
All right, so as Derek just mentioned, a lot of these irregular galaxies are caused by collisions of two or more galaxies. So here's a great simulation we found that simulates both the Milky Way and the Andromeda galaxies colliding. So you might be thinking the Milky Way galaxy, isn't that the one we live in? Yes. And basically what's predicted is in the future, the Andromeda galaxy is spiraling towards us. And at some point, these two will collide. And this process has been seen in other galaxies. And this is a great simulation of what could happen to both our galaxy in the future, but it also shows how some of these irregular galaxies can be formed. So Derek, if you want to play that and see if it goes. Yeah, so there's the Milky Way, nice spiral galaxy. And then over the course of billions of years, Andromeda is actually getting closer and closer to us, which is interesting because in the universe, we think of most things moving away from us or expanding. We also have the Triangulum galaxy, which is also part of the local group. That's a much smaller one, but that is also very close to the Milky Way as well. So let's see. As they get closer and closer, gravity starts to pull them in. What happens is you get these huge tails, which look really cool. And we can actually see this process in other galaxies throughout the universe. So usually they get some sort of initial passing, and then gravity sort of pulls them back together, and so on until they start to form one galaxy. And so that's how the process of how many of these irregular galaxies can actually be formed. All right, I think you can go to the next one. If it'll cooperate.
Yes, it cooperated. So here, what is some current research done with irregular galaxies? These can be separated into four main questions. The first is, what regulates star formation in irregular galaxies? As we discussed prior, spiral galaxies tend to have high star formation because they are young and they also have very dense gaseous arms. Ellipticals, on the other hand, have low star formation because they're old and not as much gas. Irregulars tend to have higher star formation, but with no structure. So what regulates the star formation? Why is the star formation very high? That's an active research question, which Mason will discuss later on in the talk. The second big question is, how do dwarf galaxies form and get their shape? This is a very interesting question, mostly because dwarf galaxies, as discussed, they are they're smaller galaxies, and they're also thought to be the types of galaxies that formed when the universe first started forming galaxies, which was like over 10 billion years ago. So that can provide some insight into what the universe was like all those many years ago. And the very, very short answer is that they're thought to form in a complicated way that has to do with galaxy and thermal pressure, something that I will talk about the current state of that research in the future of this talk. The third question is, what are the consequences for a lack of heavy elements? Or in other words, what are the consequences as to why there is low metallicity in irregular galaxies? As I discussed earlier, spiral galaxies have a lot of gas and therefore a lot of elements, and that regulates the size and the total number of stars of spirals. But for irregular galaxies, this is not the case. There is not really a connection between the lack of heavy elements and however many stars are in the galaxy. And this is very similar to the first question as to what regulates star formation. So kind of questions 1 and 3 kind of are in the same realm of astrophysical research. And metallicity is a very interesting question because it dates back all the way to the Big Bang, where the elements were first thought to form. So that's another active area of research in irregular galaxies. And the last question, which is a much more recent question, by recent I mean in the last just 5 years, is, can irregular galaxies provide insight into cosmology? And the answer is generally yes, but we've only just realized that they can be of use. And this is mostly because irregular galaxies are described by some very simple physics, which I will discuss later on. And it makes them a very easy probe for dark matter distribution. And you might be thinking, oh, dark matter, that's a very interesting topic. Turns out irregular galaxies are very relevant to the search for dark matter and can illuminate some of the theorized properties of a mysterious particle or not a particle. So I'll hand it back to Mason.
So here is some lovely pictures of irregular galaxies, because of course, when you study astronomy, that's all anyone wants to see is of course the pictures. So what you can see amongst all these irregular galaxies is generally you can see the presence of two galaxies, sometimes in the process of colliding, sometimes this is when they're about to collide, sometimes this is after they have already collided. But one thing that is interesting is this irregular galaxy kind of definition here is a broad. You know, for spirals and ellipticals, they have more defined definitions. These can irregular galaxies can account for many different types of galaxies. Some of the most interesting ones, if you want to flip to the next slide, Derek, are these ring galaxies. Let's see. Yeah, so we have these smaller and larger galaxies colliding. And basically, as they're colliding, as you'd expect, there's sort of a shock wave. And so ripples appear throughout the galaxies. And this pushes all these gases and the stars and the dust outwards. It makes these very interesting rings of materials. This is a hotbed of star formation, as you have all this material concentrated in single locations. We also have, on the next slide, some of these more in the process of colliding antenna galaxies. And so this one, these are a pair of galaxies that used to be spiral galaxies until they collided. You can see the more zoomed up photo on the right, and on the bottom left, this is more a zoomed out photo. And what you can see in that more zoomed out photo is the large tails that formed, which we kind of saw in the simulation earlier, meaning they probably passed each other before they're getting gravitationally attracted towards each other. And again, this is a great preview of how the Milky Way and the Andromeda galaxies could look in several billion years. And basically, the process of collision is causing billions and billions of stars to be formed, just the interactions between the two galaxies. And that's seen with these kind of red highlights on the right image. All right, you want to hit the next slide? Two very important irregular galaxies are the Magellanic clouds. On the left, we have the large Magellanic cloud, and on the right, we have the small Magellanic cloud. The reason these two galaxies are important is because they're actually dwarf irregular galaxies that orbit the Milky Way. So essentially, these are our closest neighbors in space to the Milky Way. These are again called dwarf galaxies. Let's see if you want to hit the next slide. So the more interesting one is probably the large Magellanic cloud because it has this huge star forming region called 30 Doradus, sometimes called the Tarantula Nebula. And that's seen in the bottom right. And here, millions and millions of stars are being formed. In fact, most of star formation in the universe at this point in time is actually led by dwarf galaxies, these smaller ones. Because of their proximity, you can actually see these with the naked eye. You do have to be in the southern hemisphere, so travel to South America or Africa or Australia. Those are good places you can actually see at night. And again, there's this prevalent theme of having star-forming regions in irregular galaxies. It's not always true that all irregular galaxies have high star formation rates, and in fact, this is something that is currently debated, but it is a general trend that we do see to some respect. All right. Next slide. Here is another irregular galaxy. This one is known as M82, seen in the top right. Now, we have the normal disk, which is kind of that lighter greener material in the center. But we also have these large, what are called outflows at the top and bottom of the plane. Those kind of red or blue would appear to be gas being ejected out of it. So what causes this? So the main reason is in your galaxy, you have supernovas, you have an active galactic nucleus, you have stellar winds. And essentially what happens is they're literally pushing material and gas out of the star forming region of the galaxy, which is at the very center, kind of like the source, and they're pushing it outwards into space. This regulates star formation as, of course, in order to create stars, you have to have this gas and material in order to condense and form stars. And so these outflows, in fact, limit star formation. This is a high star forming galaxy. as a result of M81, which is seen in the bottom right, passing very close by to M82. M82 is also known as the cigar galaxy. And that's, again, you can see it on the bottom left, or sorry, the bottom left of the bottom right image, which is that smaller galaxy zoomed further out. And so on the left here, we have a diagram of how these outflows actually work. And the main thing is there's kind of a, like you have on Earth, a carbon cycle or an oxygen cycle, there's a gas cycle that occurs in galaxies like this. And of main interest to me in my research is these orange galactic outflows, which are pushing this material outwards. So if you can hit the next slide, please. So what is actually interesting about these outflows, apart from star formation? How can you actually measure them or visualize them? So if you look through your telescope, and this is a high-powered telescope, mind you, like the Hubble Space Telescope, you can observe at different wavelengths how bright an object is. This gives you something called a spectrum, basically a measure of how bright an object is as you look at it for different wavelengths. Now, as you have this major star-forming region of your galaxy, your source, it is emitting photons, or essentially light waves outwards, which is what you, as the observer, want to see. Because of the presence of heavier metals, and remember, as Derek said, metals can refer to anything bigger than helium. A lot of the times is referring to silicon or magnesium, elements like that. If the photons are at a certain wavelength, they can be absorbed by these ions like silicon. And as such, the silicon changes energy states, but what happens is the photons, basically the light at that specific wavelength, is essentially absorbed by this galactic outflow, by the presence of these ions. And so if they're absorbed, what you get is a dip in the continuum. Now, once absorbed, of course, it could be re-emitted. And re-emitted can result in more of a spike in your wavelength, as more photons are emitted at those certain wavelengths. So if you have your large expanding outflow, you can think of it as concentric shells having basically different radii, envelopes. What you can have is both absorption and emission occurring. And what you get is this bottom left profile here, when you add the two together, and you get what's called a P-sigma profile. And a simulated one is seen on the right here as well. Now, the actual wavelength that photons are emitted are right at the middle point, that zero normalized velocity. Absorption occurs between the source of the star, or sorry, of the galaxy, and the observer. Since absorption occurs in between, you get what's called a blue shift, which means the actual wavelength that things are being absorbed, because they appear moving towards you and they're closer to you, get absorbed at a slightly bluer shift. You can think of that as being towards the left of the wavelength in these plots. Emission can occur both blue shifted, as the absorbed material can be emitted again in between you, the observer, and the source, but it can also be red shifted. So as you saw in the previous picture of the M82, it kind of behaves like a bicone, and material is thrown out not just towards the observer, but also away from the observer. You can't see any absorption if you're not in between the source and the observer, but you can see re-emission if it gets re-emitted back towards you. This is called a red shift, where this emission occurs further from the source than the actual source itself. And we have a couple examples on the next page too. These are different silicon plots due to different ionization states of silicon. And so you can see these absorption profiles, and some of them also contain emission, which you can see in the top left and top right. The top left and top right are the result of silicon 2. And as I said, they occur at those specific wavelengths, in this case, 1260 angstroms and 1190, 1193 angstroms. In the bottom right, we have silicon 3, which occurs at about 1206 angstroms. And on the bottom left, we have a silicon 4, two different ones that occur at 1393 angstroms and 1403 angstroms. These are significant in themselves because these are actually ultraviolet observations done by Hubble. Ultraviolet is significant because if you're observing something from Earth, ultraviolet radiation is blocked out by our ozone layer, keeps us safe from the sun, which is a good thing. But these specific lines of silicon are actually only available, or they only occur at these specific wavelengths. So if you want to observe them, you're going to have to use a space telescope like Hubble. Yeah, so those are just some interesting things that outflows do. They are prevalent in irregular galaxies like M82, but many galaxies with star formation have these as well. So it doesn't necessarily have to be limited to just irregulars. But this is a very relevant area of research at the moment. And here is another galaxy, UGC 5189. What's important here is we actually have data from two different sources. So if you look at a galaxy in two different wavelengths, say one in the X-ray and one in the optical, you get actually two different photos. So galaxies can actually look different depending on which wavelength you're looking at them through, due to what type of radiation is being emitted by the material in the galaxy. So in this galaxy, these bright purple objects are taken in the X-ray, and this is from Chandra with their X-ray telescope. And this bright purple source at the top is actually a supernova, which was observed in our rest frame, the Milky Way's rest frame in 2010. But all these red, kind of green and blue stars that you see in the background, those are actually just optical photos taken by the Hubble Space Telescope. So you can actually get two different photos of the same region in space if you look at it through different wavelengths. All right, Derek.
Yeah, thank you, Mason. So here's another example of an irregular galaxy. This is NGC 1427A, which was shown earlier. And coming back to it, the reason why we think it's so important, because it is an interesting galaxy in its shape. It's one of the more weirdly shaped irregular galaxies. And as a result, there's a lot of research going into how it actually formed. So NGC 1427A is a galaxy that is located 51 million light years away in what is known as the Fornax cluster. And it is a dwarf irregular galaxy, meaning that it is supposed to be reminiscent of the early galaxies that formed in the early universe when galaxies were first taking shape. And what current research seems to suggest is that gravitational forces that are from the neighboring galaxies, recall that this is located in a galaxy cluster, so there are other galaxies around it, they seem to exert a tidal force on the galaxy that then creates its irregular shape. So this is important because in the early universe, when galaxies were first forming, it was very dense, and likely gravity was the thing that then formed some of these small galaxies and created their irregular shapes. Now that's just the prevailing theory, and this study was very recent in the last 2 years, and there's much more research being done on this galaxy especially, largely due to the fact that it's located in a large cluster. The next galaxy that I would like to talk about is AGC 198691, which is not a very fun name, but it is the most metal-poor galaxy ever discovered, meaning that it has the least amount of elements heavier than helium of any galaxy discovered. This galaxy is a dwarf irregular galaxy again, and it's located in the Leo Minor constellation, which is 370 million light years away. Given its status as the most metal-poor galaxy ever discovered, it is of specific interest to scientists and astronomers who want to look at how galaxies have formed and specifically how their stars were formed. Since dwarf irregular galaxies are similar to the first galaxies in the universe, you can do this by constraining how much helium is present in their galaxy. So if you take a look at the photo, this is of the galaxy, it appears very blue, which means that it is a very young galaxy. And that means that most of its elements that are present in the galaxy are present in its stars. And since we know that it has very few metals or very few elements heavier than helium, we know then that we can get a measurement of the elements of hydrogen and helium that would tell us exactly how much mass initially formed in this galaxy. Now, the Big Bang, which is how our universe began, suggests that around 25% of all the mass that was created was initially helium. When we look at measurements of this galaxy, it is found to be 24.5% helium, which is in agreement, considering that this galaxy is supposed to be representative of some of the early galaxies in the universe. So this is some strong support for the Big Bang theory as to how the universe began. And as a fun fact, this galaxy was actually discovered by a team that included one of the University of Minnesota's own Evan Skillman. So there's a little bit more of a personal nature for this galaxy. And the last galaxy that I want to talk about is called the Wolf-Lundmark-Milot galaxy, or the WLM galaxy. This is actually a very close by galaxy, only 3 million light years away. And it is a type 1 irregular galaxy, as it shows a bar-like structure in the center, which you can see in the image on the right. And as a super random fun fact, this galaxy was discovered in 1926, so it has been around for quite a long time. And in the TV show Doctor Who, the New Earth Republic attempts to actually colonize this galaxy. So that's something that you can think about. So this galaxy is being used currently in research, mostly in the search of dark matter. Another weird thing about the WLM galaxy is that it has an asymmetric rotation, which means that one side of the galaxy rotates faster than the other side of the galaxy. So apart from being a weird feature of the galaxy, it is also makes it very easy for astronomers to constrain how much dark matter is actually present in the galaxy. And as a quick rundown of how one can do that, dark matter can be used, or dark matter profiles and where they are in a galaxy can be discovered using the rotation curves of each galaxy, or how fast the galaxy is actually rotating. So since we know that it is asymmetric, we are able to very easily understand the dark matter distribution. And very recent attempts to then use WLM as a baseline for future dark matter maps of irregular galaxies, and it is proving to be very useful. So there's a weird theory with dark matters that says that if they are particles, then they can self-annihilate into gamma rays. So if you measure the gamma ray signal from this galaxy, you can, in theory, measure how much dark matter it is, and it would be an indirect detection of a dark matter particle, which is of much significance for the world of physics. Currently, this obviously has not been discovered yet, but there's active research into the use of irregular galaxies and their dark matter profiles in order to hopefully one day discover that elusive dark matter particle. So, to conclude this talk, irregular galaxies are obviously very beautiful. We've shown a great bunch of images of them, and they have been fascinating people for the last 100 years of astronomy. They offer a probe into various areas of physics. As I talked about, they offer some proofs of the Big Bang and also some evidence of dark matter, and also how galaxies and stars form throughout the history of the universe. And it is still a very active area of research, both here at the University of Minnesota and all across the world in many areas of astronomy. So that will conclude our talk. We do want to ask, or if you have any questions, please post in chat, and we will stand by because there's a delay in our stream for about 2 minutes to answer any questions that you may have.
Looks like it's about a minute delay. Yeah. All right, you just concluded on the YouTube. Derek, in what episode of Doctor Who was that thing from?
I actually don't know. I read that just in passing. I thought it would be fun to mention though.
Someone mentioned it in the chat. Yeah.
Yeah, I'm seeing. Yeah, you can go find it. That would be great.
Oh, it's a novel.
Oh, it's from a novel. Okay.
Yeah. The Synthespians
Interesting.
features the Sixth Doctor.
I'll have to check it out then.
Yeah.
Okay, if there are no further questions, then we will end it here. So thank you so much for listening, and we hope you have a great rest of your night and also holiday.
Thank you, everyone.